Today we cover two topics. The first one is called percent composition, and the second one is called simplest formula or empirical formula. And they're actually related to each other. One's sort of the opposite of the other one. Both of them have to do with describing compounds. Percent composition is just a list of the mass of each element as a percentage of the total mass of the entire compound. So we could define it this way. We could say your percent composition is equal to the mass of the element divided by the mass of the compound. And then to make it into a percentage, of course, you have to multiply by 100 because it'll just be a ratio if you don't. Here's an example. Water's mass is 11.19% hydrogen and 88.81% oxygen. Now if you think about water being H2O, you think about it should be about 2/3 hydrogen and about 1/3 oxygen. And by moles, that's exactly what it is. But by mass, it's not, because hydrogen and oxygen weigh different amounts. So if we're going to describe by mass, we have to actually be able to calculate this stuff. How can we do it? Well, to find the percent composition from the formula, here are our steps. The first thing you want to do is multiply the molar mass of each element that's in the compound by its subscript in the compound. Then add all the element masses up. Well, you'll have the total mass of the compound in 1 mole. In other words, you'll have the molar mass of that compound. Then finally, you take the mass of each individual element and divide it by that total mass that you just found, and then change it into a percent. So let's do an example. Let's find out the percent composition of both lead and chlorine in PbCl2. So for lead, I'm going to take 1 mole, because its subscript is 1, and I'm going to multiply that by the molar mass of lead, which is 207.2 grams per mole. That, of course, just gives me 207.2 grams. For chlorine, I'm going to take 2 moles, because it has a subscript 2, and I'm going to multiply that by a molar mass of chlorine, which is 35.453 grams per mole. And that's going to give me 70.906 grams of chlorine. Now, if I add them both up, I come up with 278.1 grams. That's the molar mass of PbCl2. It's also the mass of 1 mole, by definition. So to find out what percent of this compound is lead, I take the mass of lead, 207.2 grams, and divide by the total mass, 278.1 grams. That's going to give me a fraction, and multiply by 100, and I'll have a percent. This works out to 74.51% to 4 significant figures. I'll do the same thing for chlorine. The mass of chlorine was 70.906 grams, and I divide that by the total, 278.1 grams, and then I multiply by 100. Well, that gives me 25.50%. A quick check is you can always add these 2% together, or 3%, or however many it is, and it should come out to about 100%. And if it doesn't, that's a good indication that something's gone wrong. You try one. Find the percent composition of all 3 elements, carbon, hydrogen, and oxygen, in aspirin, which is C9H8O4. Stop the video, give this your best try, and I'll come back with an answer so you can see if you've done it right. Okay, starting out with carbon, I have 9 moles, because that's my subscript, and I'm multiplying it by the molar mass of carbon, which is 12.011 grams per mole. That's going to give me 108.099 grams of carbon. For hydrogen, my subscript is 8, and the molar mass of hydrogen is 1.008 grams per mole. That gives me a total of 8.048 grams. Oxygen, subscript is 4. Molar mass of oxygen is 15.999 grams per mole. That adds up to 63.996 grams. So if I want to find the mass of a mole of this compound, I add all 3 together. That comes out to 180.143 grams to the nearest thousandth. Now, to find percent composition, for carbon, it's 108.099 grams divided by that total of 180.143 grams. And then expressed as a percent by multiplying by 100, I end up with 60.007%. to 5 significant figures. For hydrogen, 8.048 grams is divided by the total, 180.143, and then that's expressed as a percent by multiplying by 100, and it's 4.468%. Oxygen, 63.996 grams divided by, again, it's the same total because it's the same compound, and then I'm multiplying by 100. So 35.522%. 60 and 4 and about 36 should be roughly 100, so looks like I probably did that right. Give this a try. Find the percent composition of all the elements in barium nitrate. Stop the video, write yourself a formula, and then find percent composition. Well, barium nitrate, barium has a 2+, nitrate is NO3 with a 1- charge. So after I do my swap, I have Ba, and then in parentheses, NO3, 2. So for barium, that means I have 1 mole of barium, subscript 1. Barium's molar mass is 137.3 grams per mole. So a total of course, 137.3 grams of barium. For nitrogen, every nitrate has got a mole of nitrogen, but there are 2 moles of nitrate, and so that means 2 moles of nitrogen times 14.007 grams per mole for nitrogen gives me 28.014 grams of nitrogen total. For my oxygen, well, I have 3 O's in every NO3, but there are 2 moles of NO3, so that's a total of 6 moles of oxygen. At 15.999 grams per every mole, the total oxygen mass is 95.994 grams. When I sum this up, I get 261.3 grams for the mole of barium nitrate. I have to round that off to the 10th because I don't know barium's molar mass any more precisely. Now, for barium, 137.3 grams are in a mole of the compound, but the mole of the compound weighs in total 261.3 grams. So when I divide and multiply by 100%, I end up with 52.54% barium in the compound. Nitrogen, 28.014 is the mass of nitrogen in the compound, and the whole compound weighs 261.3 grams. So that ratio is turned into a percent by multiplying by 100, and I come up with 10.72% nitrogen. Oxygen, 95.994 grams of the compound are made of oxygen, and the whole compound for 1 mole weighs 261.3 grams. So I'll change that into a percent, and I come up with 36.74% oxygen. The next concept we're going to explore is called simplest formula, or sometimes it's called empirical formula. And it's just the lowest whole number ratio of moles of each element in a compound. Sometimes this really is the formula, sometimes it's not, and it's just related to the formula. How do you get it? Well, the first thing you want to do is find the number of grams of each element in the sample of the compound. Sometimes you measure this if you're in the laboratory. Sometimes it's given to you in grams. But quite often you're going to start out with percent composition data. So if you're starting from there, if you're starting from percent composition data, they tell you what percent is, carbon and what percent is oxygen or whatever. The easiest way to approach it is assume that you have 100 grams of the compound. And if you do that, then whatever your percent is, that's mass in grams. Let's say, for example, we've been asked to do this problem. Find the simplest formula for a compound that's 26.56% potassium, 35.41% chromium, 38.03% oxygen. What we want to do here is assume that we have 100 grams of this stuff. You're just trying to find a ratio, so it doesn't really matter what mass you use, how big of a sample it is, it'll always have the same ratio. So if we assume we have 100 grams of it, then our percents change directly into grams. 26.56% potassium really means 26.56 grams of potassium in 100 grams of the compound. And we can do the same thing for the other 2 elements. Your next step is to find the number of moles of each element that's in the sample. So here are our mass quantities from the problem. We want to change these into moles. Well, I know how to change grams into moles, so I do it by dividing by molar mass. For potassium, the molar mass is 39.098 grams per mole. And so that gives me 0.6793 moles of potassium. I'll do the same thing for chromium. I'll divide by its molar mass, which is 51.996 grams per mole. And that gives me 0.6810 moles. And oxygen, 15.999 grams per mole. And that gives me 2.377 moles. In all three cases, I have four significant figures. After I do this, because I'm trying to find a ratio of one element to another, my next move is to divide all the numbers of moles by the smallest number of moles. Then that smallest number of moles becomes 1, and everything else gets compared to that. Back here at my problem, I realize that the smallest number of moles here is the 0.6793 moles of potassium. So I'm going to divide all three quantities by that number. Obviously, I'll just get a 1 if I divide 0.6793 by itself. I'm going to get something pretty close to 1 if I divide 0.6810 by 0.6793 moles. And in fact, that's 1.003. And when I divide 2.377 moles by 0.6793 moles, I will get 3.499 for my ratio. The next thing to do is to round off all the ratios that are within a few hundredths of a whole number to that whole number. And then if there are any remaining ratios that can't be rounded to a whole number, I should round those to the simple fraction that they're within a few hundredths of, like a half or a fourth or a third. So 1.003 is within a few hundredths of 1, so I can just round that to 1. But 3.499 is not within a few hundredths of any whole number. It is, however, within a few hundredths of a simple fraction, 1/2. 0.499 is pretty close to 0.5, so I'll round that to about 3.5. The next thing to do is to multiply all the ratios by the smallest integer, that's the smallest positive whole number, that's going to make them all into whole numbers. So in this case, I want to get rid of a half. 3.5 is actually 7 halves. If I multiply everything by 2, I'll get rid of my half. So I multiply 7 halves by 2, I get 7. If I multiply 1 by 2, I'll get 2. And then I'll multiply this one by 2 as well and get 2. So now I've converted them all to whole numbers by multiplying by the smallest integer that will make that happen. And then those whole number ratios that I get, well, they're the subscripts in the simplest formula. So for this compound, I had a 2 for potassium, so that makes it K2, and a 2 for chromium, so Cr2, and a 7 on oxygen, so 7. Okay, you try one. Stop the video and try to find the simplest formula for this compound. It's 52.14% carbon, 13.13% hydrogen, 34.73% oxygen. I bring you an answer, but you want to try this out yourself first and see if you can do it. Well, the problem said for carbon I had 52.14%, so that means in a 100 gram sample that's 52.14 grams. And then for hydrogen it was 13.13 grams, and then for oxygen in a 100 gram sample I'd have 34.73 grams of oxygen. I'm going to convert all these to moles. That's the first thing I want to do by dividing by their molar masses. So for carbon, that's 12.011 grams per mole, and the result that I get is 4.341 moles to four significant figures. Hydrogen, 1.008 grams per mole. So that gives me 13.03 moles of hydrogen in a 100 gram sample. And in the same sample, for my oxygen, I divide by 15.999 grams per mole, and that leaves me 2.148 moles of oxygen in that sample. Next, I'm looking for the smallest number of moles. Well, that's the 2.148 moles of oxygen. So I'm going to divide the other two mole quantities by that, 2.148 moles. When I divide 4.341, I get 2.021, and that ratio is within a few hundredths of 2, so I round to 2. When I take 13.04 and divide it by 2.148 moles, I get 6.066, which is within a few hundredths of 6. So I already have whole numbers here. This, of course, is a 1, and I don't need to multiply by anything. I can just write down C2H6O, or O1. Well, if you had trouble with that last one, maybe you can do better this time. Find the simplest formula for a compound that's 32.38% sodium, 22.65% sulfur, and 44.99% oxygen. Stop the video, do your best, and then check my answer out. Well, going off my percentages, sodium, 32.38 grams, because it's 32.38%. For sulfur, it's 22.65 grams in 100 grams of the compound, and for oxygen, it's 44.99 grams in the compound. Next, I'm converting them all into moles by dividing by their molar mass. For sodium, that's 22.99 grams per mole, and that works out to 1.408 moles of sodium. Sulfur's molar mass is 32.064 grams per mole, and that works out to 0.7064 moles of sulfur in 100 grams of the compound. For oxygen, it's 15.999 grams per mole, and so in 100 grams of the compound I'd have 2.812 moles of oxygen. Next, I'm looking for the smallest mole quantity, which is the sulfur mole quantity. I'm going to divide them all by that. So when I divide 1.408 by 0.7064, I get 1.993. That's within a few hundredths of 2, so I'll round it to 2. Dividing 0.7064 by itself, of course, gives me 1, and dividing 2.182 by 0.7064 gives me 3.981, which is in a few hundredths of 4. So my subscripts are going to be sodium 2, sulfur 1, which I won't write, and oxygen 4, Na2SO4. Now this is an example of an ionic compound because it has a metal in it, and SO4 you might recognize as the sulfate ion. For an ionic compound, the simplest formula is the formula. There is no other formula. The smallest whole number ratio is the ratio. The smallest whole number ratio is the actual formula for ionic compounds. For a molecular compound, in other words, something that's made all of nonmetals, the simplest formula may be the formula, or it might not be. Here's an example. SO3. SO3 is the simplest formula for, of course, SO3, but it's also the simplest formula for S2O6 because the lowest whole number ratio in S2O6 is SO3, or S3O9, that's also SO3, or S4O12. All of these have the same simplest formula, SO3. So for molecular compounds, simplest formula may not actually be the formula, but it's related because these things are all whole number multiples, 1, 2, 3, and 4 times SO3.